water, because energy and water are so closely linked. We use an awful lot of water to generate our energy from the fuel process through the operational process and in our use in various commercial endeavors and in the residential environment. The flip side is that in order to have water, we have to use a lot of energy to pumping, transport, and conveyance, and treatment, both for distribution, creating clean water, and then dealing with the discharge when we're finished with it. Nationally, we use about 3% of the electricity used in the United States is used just to move and treat water. In California, it's 19% when you add the end use, and that's also 32% of the natural gas used in the state of California is just water related. Just to give you an idea, that kind of a representation is equivalent to the pulp and paper manufacturing industry in the United States. So NREL, the National Renewable Energy Lab, is somewhat unique in the Department of Energy world in that because we're focused on renewable energy and the deployment of renewable energy technologies and energy efficiency, we actually have to look across the entire portfolio of our nation's energy technologies. Sustainability being an important key feature of that, we actually deal with water as part of our normal mission, from things like life cycle assessments of the environmental impacts of different energy technologies, looking at water use by individual technologies, conservation programs, and efficiency. So in a way, water is very important to us as part of our daily activities. So when we think about nationally, somebody mentioned biofuels earlier. I know you can't see all the little data points on here. What we're looking at is a graph that was from the report to Congress that the National Labs provided a few years ago. And from bottom to top, we're looking at different pieces of processes of our energy system. From the bottom in black are coal mining, coal washing, slurry, etc. In the brownish colors are things having to do with oil. And as we move up, we move into some of the more novel and new fuels. And on the horizontal is a logarithmic chart looking at the water intensity of each of these processes. And if you just kind of step back, you can see that if you go from bottom to top, things move from left to right. These are order of magnitude increases in the amount of water used. When we get up to hydrogen and biofuels, you can see that our modern fuels are extremely water intensive unless we change how we do that. NREL is looking in great detail at the water requirements of individual energy technologies. Going from right to left, and I know you can't see the individual things, I can see it, and that's almost intentional. You can look at the different processes for electricity generation mated with their cooling systems. For coal on the right, moving to the left, we have natural gas, and depending on what kind of a cooling system, it can be very water intensive or not so water intensive. Nuclear, depending on if you're going to an open loop or closed loop system, can be very different in its water intensity. And way there on the left are our renewable technologies. The farthest left ones are photovoltaics and wind. Basically, you don't use a whole lot of water to generate electricity using these technologies. The ones towards the middle are concentrating solar. Concentrating solar looks an awful lot like your typical thermal electric generation if you use traditional cooling technology. So we're working a lot on reducing the water use, looking at hybrid and dry cooling opportunities, which would drop the water use for these new renewable energy technologies. But when you think about the deployment of large-scale wind, for example, in the Midwest, you're displacing traditional fossil or nuclear power sources that are extremely water intensive with something that doesn't use water at all. Research, we conduct research on individual technologies, biofuels, geothermal, and the others that are listed there. Everything from looking at the fuel source to water and energy efficiencies and the processes for generating the energy, looking at both the environmental impacts and the sustainability metrics associated with our future energy choices. We also do a lot of work on implementation, from the policy side to integration of different types of technologies with our existing infrastructure, informing ideas as to how our new infrastructure that look at the energy and water flows in both commercial and residential buildings and processes. Also develop a lot of modeling tools and other devices that are available in many cases over the web for people who want to do some scenario planning. And here's a list of, it's just a list of all the kinds of tools that are currently available that range from individual building community design to analysis of market economic impacts, systems integration. But we also have such practical things as something called In My Backyard, where you can dial up on a Google map your house or your plant and draw on it the size and shape of a potential TV array, for example, and find out the economics of PV for your zip code, because it also includes some of the policy incentives and implications, similarly for wind. We don't have that for every renewable because most people aren't thinking about putting a geothermal plant in their backyard. But these are the kinds of tools that are very useful for a small corporation, for example, looking at the trade-offs for various implementations. We also are and another plug is the Department of Energy has funded something called the Open Energy Information Portal, which is a website where many of these commercially available or commercial implementation tools are available for use. Just go to OpenEI on the web, and you can explore opportunities for application in your own arena. And I think I'll stop there. Again, sort of a broad overview. We generate the tools that people like you can use.